And so one paper that does it, two causal principle for improving visual dialogue. What they're doing here is that they're making observation, and I'm going to share these. And so they take this problem here, and they're making two observation, and these are empirical observation. Although they're motivating it through theory, but originally they were empirical, just like the model performed better. And one interesting one was that this history linking it directly to answers may be something hurtful, and may unfortunately allow the neural network to learn shortcuts it should not learn. Because it then not generalize well. And then the other one, which I think is, if anything, the most interesting, is the concept of confounder. And I will discuss it more in a second. Let me just talk about the first one. Like, the idea here is that you have a history and you want to get the answer. And there's this very interesting kind of folkloric knowledge in neural network, or even in multimodal, and I'm probably one of the people also sometimes pushing for that. I'm like, multimodal, more modality is always better, or more information is always better, and let the network learn, but give all the knowledge you have, or give it all the input features you have, and let the model learn it. Here, the concept is that maybe adding always more data, more information may not all be helpful. And they empirically saw it, that although you want to predict here, you adding the history again, like, because the history of the dialogue was already used to get a better representation or better understanding of the question. And usually it is because there's some pronouns and they are hard to disambiguate, but with the other history, it's helpful. And then to know where to look at in the image, you also look at the history. But you may think, hey, why not, when it's time to do the answer, why not put the H again? And it worked better on some data, so hey, I will do it always. But here, what they found, which was really interesting, is that if you have a history of the dialogue, you have a question and you like to answer, when you put this baseline, when you put this, when this link is there, what this end up learning is that it end up learning that the answer that you want is in fact an answer that is the same length as the previous answers. It's interesting, huh? It's like, what they end up learning is that, like, hey, it's just because I've seen all these previous answers, I probably want an answer that has the same length, just because that's the way this person was speaking, or this annotator was doing it. When you don't put it, then you get answers that are there mostly not because they look like the history of previous answers. All of these are answers for very different questions, so that there should not be knowledge that are used just because I phrase things differently. Like, you want not because it has the same number of words, you want to just put it as a good possible answer. And so that's what they were seeing, is that if you're not careful, there will see a correlation with the length of the question, with the length of the history of the question, with the length of the final question. And this reduces that one here by removing this link. The more interesting of causality, and I need to bring a new concept that I have not explained yet, which is the concept of confounding variable. And let me just talk about confounding variable before I talk about the specific for that paper. Confounding variable is, we may think in certain cases, because we look at data and we're like, hey, every time, I should have prepared a good example. I don't know. Every time I see, let's go with this. Every time I see this question, I get this answer. And so I may think that the way the answer has been phrased is only to be able to answer the question like that. In a sense, that's a causality I would like. I would like the answer to be mostly based on what the question was. That's the causality of that. But there may be some confounding variable. And in our case, is the data set were created with the same annotator, or some, at least maybe creating both the question and the answer. That would be one possibility. Is like, or at least the user or some other cause, let's say, but one version would be if the same person created both, or then it looks like there's a causality between them, but really it's just that both were just created with the same. And so that's a confounding variable, and that's very hard. That's one of the hardest thing in causality, is like something you see a correlation, but is it really causality? There could be another confounding variable that makes it so that it looks like they're related to each other, but it's not, because one caused the other. So that's the idea of confounding variable. Confounding variable may be okay to model, but there's also sometimes, like in the example that of visual dialogue, that's the case, is you can have a spurious relation with Q&A. So it's like maybe effectively there's some effect, like Q is causing A, but there's maybe on top of it, you may also have kind of a noise, and it's adding a noise. But if it was just white noise, then we could ignore it. But here you're adding this kind of bias that in the data, and so modeling it explicitly will, and that's the key of the solution, is modeling it explicitly. If I don't have it and I just model HQ&A like usual, then it's going to be much harder for my algorithm to really learn the real causality, because there's some confounding. But if I allow my model and I explicitly have that confounding variable as a path, then my hope is that this will help the learning and the optimization. And so in our case, the U will also be unobserved. There are cases where that confounding variable, we're lucky and can be observed. In our case, it's going to be latent in this. And most likely, the intuition is that because answers could see the history, and so I gave an example earlier, maybe the same person created both. But here, in this case, at least that's the hypothesis from the author, is that maybe the people who created the answer, they could look at the history. And so they can look at the history, and so there may be a bias in the way they phrase the answer, and that becomes a confounding. And so the example of confounding example will be, in this case, is this context he. So like you have a person pausing in the front, mountain of a gear. That's the first initial. Is the person a girl or a boy? What is he wearing? Okay, like, so we have the he, what is he, sneakers. And so in the, if you have this, like, you can go ahead and, is this context he is the topic? I expect the answer about he. And so that gives you some interesting confounding variable here. And in this case, in this context, I like to ask, are there? In this question type prefers. And so this can be trained, like this kind of backdoor can be learned automatically into the model. And so this is the example. The paper goes in more details. What I wanted to share, this is the approach they finally got, which says, hey, let's remove the link directly, but instead make it as a U variable that is there as a kind of a bias, a confounding variable. And that's the idea behind their model. And the take home I wanted for you here was to look at causality as a way to explain, or at least a way to test hypotheses, because that's the problem, is like, you know, there's maybe a bias, but how can I frame it as a research hypothesis? Now causality formalism can maybe help you to formalize these hypotheses and be able to test. That's the main take home. The details of the model, of how they did it, I leave it to you to go in the paper. That's the first take home. Another example is using the concept of causality in a slightly different way. And so I think the same way we had reasoning that was formalized in a different way. In one case, it was mostly attention. Another is about traversing a scene graph. The same thing is with the concept of causality. It's been, the word, I think, has been a word using a little bit differently. Here, let's to kind of give some context. This is the typical VQA. And the VQA here in this case is you have an image, and what is in the basket, or let's phrase first, what can be seen inside the basket? And let's say the VQA gives a remote. And what's surprising in many VQA systems is that, in fact, just rephrasing almost the same question gives very different answers. And that's a little bit troubling. And so, like, why? Probably because it learned some shortcut. So the same issue as the previous paper is like it learned a shortcut. That's most likely what happened. But how can we make the model not learning that shortcut and really learning that what the answer for that question, what caused the answer to that question, is really what a human would have also thought the same way. Not that the neural network did a shortcut because there's a remote here on the image, and that's why, like, I don't, just an example of a shortcut. So VQA may find these spurious correlation and these confounding variables exactly like in the previous case. And so the research idea here in that paper is to try to remove visual objects to see if they are confounding variable. So if really the algorithm, like, you would like the algorithm to still be able to do it, like, let's say I remove this remote, is the algorithm still able to correctly give the right answer? Because the original remote is still there. So if I remove this remote, do I still get the answer that I want? And then the interesting part is not only because there's an interesting model that will be, and so there's kind of three things. One is proposing a new kind of data set. But the interesting part is also have a new evaluation metric, because now you would like any VQA to still be able to correctly answer it, even if you are removing objects, at least not the object needed for the answer directly. And so what they do here is they suggest a consistency metric to study the change when a specific object is there or not there. Like, will the person correctly, like, you want the answer to be the same. So that's one. And in some cases, you remove an object and you want the answer to be different. That's another way to do this. But you want to be consistent. So whatever it should be, like whatever the human annotator tells you is the new answer, you want to be sure that the algorithm is giving you that. And so one way would be to manually re-annotate after you remove each object. Here, the idea is you want to be consistent between all questions and all versions of this. So that's kind of an approximation to the human annotation. And how do you remove object? GAN is definitely a good way. Removing object, I think we're at a point now where there's a lot of great work that's been done in removing object. And so GAN is a good way to do that. And so now what's nice is that you can, what's nice is like you can try these on all of the state of the art And then you will see very quickly, although those are differently cherry pick in the data set, but in general, the tendency is there that algorithms will have a problem. But the interesting part of the problem, the paper, is to go the next step and try to solve this. And what I like about this is that it's trained the VQA, training the model on the original VQA data set plus the synthetic data set. So you're going to train it on both, but you're consisting of images, but you're going to force it to have the same attention. So the synthetic data set are created based on the original VQA. But the data, the model to perform better, but the model itself will need to be able to use the same model to answer both. So by forcing that, you force the model to at least have less of the bias on this. So that was really interesting. Let me go a step even further and trying to go and say, let's try to understand why multimodal. I think you're probably getting a little bit now. I kind of started with like, hey, I would like to take advantage of this great work that was done in like conventional or classical AI, and that required me to do a lot in representing my knowledge so I can reason about it and maybe even do causality about it. But the reason also when I started talking about causality is I started to also like, why are multimodal model working and why are they not working sometime? I think that's really important. And I want to give another example in that direction, but here it's not using causality to do that, but it's using just an extension of the data. It's a more data-driven approach. And here is the banana ripe enough to eat? VQA will, let's say, answer that. But then, are the bananas mostly green or yellow? And then the VQA doesn't get that answer. And that's really troubling, because if really a system was to be able to know ripe correctly, they will know that ripe for bananas means that the color needs to be yellow. And if you're not answering the second question correctly, that probably means that a shortcut happened. That seems like an example of a shortcut happening. And so what can we do in this case to handle this situation that there's a shortcut? And then the idea here is to create a data set, select only the reasoning. So what they did is just a first step, which is just selecting in the VQA, just the question that require composition of perception knowledge. So there's different knowledge evidences and perception, and there's a compositionality to this. So that's a subset of the question. And then the more interesting is that they now suddenly add more questions to it. These are sub-questions that if someone answered this, you should be also answering these questions correctly. And so, and then they propose and I think this is related a little bit to the previous paper. Another way to solve the previous paper could be also with this kind of model, is to attend to the same region when answering both questions. And I think that's really interesting. So you want to be sure, and that's what the squinting model does, and that's why when I talk about the previous paper, I think I also linked these two models. But here, this model is about attending the same region when answering both the main question and the sub questions as well. And that's interesting, because then you would like it so that if all of these are about the same object, and to answer them, they all sub-question of the same thing, then you should be attending at the same place. That's a simple way. I mean, I think there's a lot of interesting follow-up to be done in that direction. This is just one way of improving the way. But I think the general idea is that you should be successful. this doesn't mean that everything is going to be suddenly performing the same reasoning as a human will reason, but at least it's a step in that direction. And I think it's at you to think of other ways to expand on that. I want to also go a little bit more like I would say fundamental question is like, what makes training multimodal classification hard? Why is it not succeeding? And that's a little bit of the original question I asked earlier in this lecture, is like, is more data always better? I mean, we talk about it with like the history of a dialogue, that more data is always made, like adding more modalities should always help. That's kind of the intuition that we have. And this is a data set example of action recognition. You have a video sequence and you're recognizing, is it which type of action, like shaking head, writing. And so these are like just an example. And you will think that in this case, if I have just the image or add the audio or add the motion, that's you could argue this is a different modality, or at least a different view on the data, because there you're looking at optical flow, which is kind of motion. And what's really interesting in this, and you, for anybody who's worked on multimodal, it happened more than once, where you work on a problem, you add a modality, and the performance is not as good. There usually it means there may be overfitting. That's one possibility, because you have more data, and I think that's a big one. The paper is trying to argue that although overfitting may be an issue, and there may be more. And so trying to think of why. So as I just mentioned, one of the possible reason is that multimodal networks are more prone to overfitting due to increase in modality and complexity. I think that's a first one. Any working in neural network, you probably get that. An interesting one is also this, which is different modalities overfit and generalize at different rates. So training them jointly with a single optimization strategy may not be optimal. So it may be that one modality, like let's say you're learning a model where you have this joint representation, and then finally trying to perform a classification task from that. Maybe not language and visual should not all be should be trained at different rates. In this case, maybe language, I don't know, maybe more discrete, more closer to the higher level representation of its semantic, while let's say the visual is maybe closer to the lower level and the texture and the appearance of the object. And so maybe it makes sense to go on one faster than the other, or spend more training on one. So that's kind of the intuition. So to address these two, there's two key ideas in this paper. The first one, which is the main building block, in fact, of both ideas, they're both building from that first idea, which is compute an overfitting to generalization ratio. And here's the idea, is that if you compute the typical like training over epoch, so this is like the loss and the epoch, and so the blue is the training loss, the red is the validation loss. This is a classic one, because usually the training always gets better, but the validation eventually can get worse. And so here the idea is to compute the distance between the two as you go along, and then compute the gap between them. Okay, so and that value will give you that the delta of these, that value will give you a gap between training. So AGR, you do it with respect to each modality, tell us how much to train that modality. So that ratio will allow us to give some information about the overfitting, because you want it to generalize. So definitely you want to get an improvement on your validation, but not at the cost of overfitting. And to find that trade-off, why not compute a ratio to this? So that's the first one, and that one I will say is not it's a unimodal, and it's not a multimodal. But the second idea takes this a little bit farther to the multimodal case, and here is that maybe some modality should be trained at different rates. But what is that rate? Because if I train a convolutional model, let's say this is a late fusion with joint representation, maybe, and I have my input for modality 1, input for modality 2, and I get my prediction, my score, and my loss. So this would be a typical convention. Their proposed approach, which is interesting, is to at the same time, it may sound like a waste because you're kind of training 2 models, 3 models, but at the same time, I'm going to also train the loss for the modality 1. I will train a model for the second one, and then I will also train the one I want, which is the multimodal one. And why did I do this? Is that by doing it on one modality, I can look at this modality and then compute the OGR for that one modality, because I can see how this modality is going on right now. Hey, is this modality just by itself? Is this modality just by itself? Is it going well? Is the validation going still in the right direction? And this one, the other one, is it going the right direction? And then I can use that to adjust my rate. And so it allows to better balance the generalization between overfitting by taking this information. So this is one idea in this on the multimodal, trying to understand what is not working and offering a way of improving on that. As you can imagine, there are a lot of other interesting research questions. Another big topic in multimodal is common sense reasoning. That's big in NLP. It's big in multimodal as well. And I think we're at the beginning of that. I mean, there's been a lot of interesting work in NLP and AI before, in knowledge also, reasoning, but their common sense has been coming back. And one direction that is relevant also to some of the projects in the class is looking at it, common sense, as part of emotion, and looking at it in the case of dialogue. So in dialogue, the emotion can be often just be based on currently the current representation, but also based on the context of the people before. And so the context is important, but it's not just context, and that's what this paper on common sense is trying to push, is that it's not just this context. The way of formalizing the context may be through some kind of aspect of common sense. Is like, you know, that if someone is laughing at you and you were already sad before, then you're gonna get probably angry afterward. So this the kind of common sense that you can expect. That's the kind of thing you would like to model. So the proposed model is approach is for each utterance, try to infer not only the intent of this, but also the effect on the speaker and the reaction. So you're not only trying to predict, hey, my emotion, but also what just said will have an impact on the other person I'm talking with. And to do that, what's really nice is the author took the time to create an extension of their data set, the MEL data set, where it's not only looking at the emotion or also the intent or the emotion, but also it's not just about the emotion, but what was really the intent behind this. So it's kind of a pragmatic. So this level is more on the pragmatic side. And then here, more on the interpersonal side, like what is the reaction? And that's a little bit the common sense that comes also there. So here, the common sense, at least argued by the authors, will be like on like when you do the pragmatics, there's maybe a need for common sense. And when you do the interpersonal, like or the dialogue, you may need as well. And so a person says something, look, it's beautiful outside. Why are we arguing in an angry way? But what is it really the intent? And so that's the kind of extra information. And just to get a quick hint, in fact, for time purpose, I may not go into detail. The main thing is that they integrated this Comet. So if I realize I didn't talk about this model, but one computational model of common sense relatively recently, that was Comet as a way. And so this model tried to add this. The rest of the model is more typical, where you look at the previous state and the state of the other person and use that to predict the next prediction. So I want to bring one more aspect, and then the last few take home, I may need to just give you the high level version of that. But one thing is about coherence. Coherence is an interesting topic. It's a little bit related to common sense. In this case, it's provide the relation between two spoken or written sentences. And so coherence provide information about how the content of discourse unit. So discourse, different sentences or discourse unit. And so the interesting part of this data set that was shared and the research task is that let's try to at least formalize that. It's like, and there's been a lot of work in just language about coherence. It's like, is this sentence coherent with this sentence? And so that's the first question. Is it coherent? But a more interesting, like, what is that relation? How is it coherent with each other? That's even more interesting. And so if I say this image and this sentence, like horse riding, jumping a fence, is like, what is the level of coherence between it? It's maybe just a very fine-grained description of what is being, while meta could be more like about a meta, higher level understanding of that relationship, or it could be an opinion, or it could be telling a story. So these are different ways that discourse could be, and the coherence could be encoded in the discourse. And so the novelty of it is to not do coherence, not just in language, but do it in a multimodal between language and their caption. And from that, they managed to get a great data set for you if you want to look at on this. So I know we're almost out of time, so I'm going to do this one last one because I think it's a very, very important one, and we'll have a full lecture, guest lecture on this topic. Many of these topics I talk about will be things we'll revisit through the guest lectures after the midterm. So we'll be able to go in more in detail. But social impact is one. I think it's very important when we're building all these multimodal models to be aware that there could be like biases in it. And we talk about different ways of detecting biases, and in some of the other papers, the biases was detected mostly to try to get better performance. That's one way. But also you want to look at biases because also these biases could have an impact on people's lives. Like an example, like if we use a system that look at YouTube videos or some multimodal videos to decide to hire or pre-screen the resume, that can be very dangerous if not done in a transparent way and interpretable way. So the interest in the community has been really in creating these data sets, both language and also with images and sometimes with videos, to try to reduce the potential bias. And there's a great demo at ICMI this 3 weeks ago on this topic, and I think there's the data set is shared also on this, which look at like one of the most important but also well documented is about gender possible biases that you can see, and they see a significant difference in predicting distribution with respect of gender. And the other example is about misinformation, what has been popularized under the term fake news. I think this is another aspect that is very important. And so you want to be able to, and there's another interesting data set that is multimodal, also with language and their images as well. So I invite you to look at the last 4 papers, look at emotion as a way to engage people more in this. And the last one is looking at multilingual and looking at aspect of multiple culture. You could go all the way, but for now, just multilingual. So if you want to go and look in details, I put all of these papers, and these are all the last year. Most of them are the last year. That's the kind of recent trends that we've seen in a multimodal. So thank you very much for your attention.